First of a few videos on dispersion, which is another means by which we can describe our data that will complement our ability to do so using central tendency. So when we think about dispersion, this is a synonym for variability, and variability is found throughout the natural world, and it's oftentimes expressed through visual means in different types of graphs, including some of those that we talked about in previous videos. Here we've got a bar chart, and the variability or the dispersion in data is expressed through these error bars. The taller the error bars, the more variability or the more dispersion that we have in the data. Another valuable means of displaying how much variability we have in our data is through box and whisker plot, which we are going to talk in more detail in this particular video. And so both the size of the box as well as the extent of the whiskers provides us with information on how much variability we have in our data set. Another example, if we're looking at a line plot, the shaded gray area here informs us of how much variability we have in our data. The further the shaded area is from the line, the more variability we have in that. And so we see variability everywhere in the natural world and in our day-to-day lives, and this tends to make things a bit more diverse and interesting. And for our data, we're going to see variability in the observations that we have. And this is going to be important because it's going to help us determine how similar or different samples or data sets are to one another. And it's going to help us to address different questions that we have that we'll be talking throughout the semester. Now, one of the challenges is if variability is too great within our data set, it can be difficult to interpret what we're observing. And so oftentimes we aim to limit the amount of variability that we have in our particular data set, and the amount of sampling that we do can affect this. And in general, the larger our sample size is, the more observations that we have in our particular data set, we typically have less variability. This is not true always, but this is true in most cases. And for the statistical tests that we're going to be covering throughout this course, understanding how much variability we have within a population and within our particular sample is going to be of value. So let's think about variability from a more practical standpoint. So let's think about a group of sharks. They live on a coral reef and they eat different fishes. Now we may have one group of sharks that only eats one specific type of fish. In this particular case, there'd be no variability in the diets of these sharks because there's only one prey item. But as we add prey items to the potential menu for these sharks, the variability in the diets of these animals is going to change. And as we add more potential prey items, we're likely to see increased variability in the diets of these sharks. So for descriptive statistics, providing some type of measure of central tendency is going to be important, so that way we can understand our typical value, but we also need to express the variability or the dispersion in our data, and to express how similar or different the observations are to one another, so that way we can get an understanding of any kind of patterns that we're observing. And the dispersion of the variability in and of itself is going to tell us how much the data is spread from the measure of central tendency. Is the data packed closely, in which all the observations are quite similar to each other, or is there lots of variability and lots of differences such that the data is spread over a wide range across the central tendency? So let's look at an example of how we can visually determine if a data set has more or less variability. So let's think about our sharks, and maybe one group of our sharks, they only consume two different prey species and they mainly eat mullet and then a little bit of red drum. And then we've got another group of sharks, same species, but maybe in a different region, and they tend to eat a more diverse prey group. So if we're interested in visually determining how variable our sharks are, we could look at the distribution of our data that mimics the histograms that we're now familiar with. And so for these sharks that eat a wide variety of different prey items, we would expect that our data would resemble something that's relatively flat and widespread. So this distribution that has a relatively low peak would be good at visualizing or expressing the data from these sharks, likely because there's going to be quite a bit of variability. And so these mimic our histograms, such that for each one of those potential prey groupings, whether they're only eating mullet, they're only eating red drum, or maybe they eat some stingrays and mullet and some blue crabs, each of those potential prey groups is represented on our histogram here, and the frequency is represented by the height of the bars. And so the more individuals that have the same diets, the taller the bars are going to be. So if we have more variability in the diets of these sharks, we're going to have more bars represented on the graph, and the total number of individuals that for each one of those potential prey groupings is going to decrease. Now, if we compare this to the sharks that only eat a couple different species, the distribution of their data is more likely to have a higher peak, so the data is going to be taller and it's going to be narrower. The reason for this is that there's fewer possible prey combinations for them to eat, and in this case, the number of individuals that are eating these possible prey combinations is going to increase. So our data is going to be more tightly packed. So we can look at a curve for our data, and this will give us an understanding of how variable our data is. The less variability, the more similar our data are, the tighter packed they're going to be, and the higher the peak is going to be, like the curve in red. And as we increase variability, decreasing the similarities among our observations, our distribution is going to get more flattened out, kind of like if we were to flatten out a pancake on a griddle, or if we're to squish a hamburger or a sandwich that's too large to fit into our mouths. Now, this is important for a lot of different fields of study, one of which that we're interested in for marine biology is for conservation. The reason for this is that as species adjust their behavior, it will then either increase or decrease the possible resources that are available to them. This includes things like diet and habitats. And so as the variability in the behavior and the resources that a particular population or species uses increases, it tends to increase their robustness to things like climate change or any kind of human impacts. But for species that are quite specialized, that have very little variability in their diets, for instance, koala bears only eating eucalyptus leaves, well, then we're going to have very limited variability, and in the event that we lose that particular resource they're relying on, they're going to be at a greater threat to potential risk. So we have a wide range of measures of variation, of dispersion, two of which are going to be critically important for this particular class are variance and standard deviation. However, we're going to cover those in the next lecture. For this particular video, we're just going to focus on range. We're going to talk about it in a couple different viewpoints. So at the simplest viewpoint, the range is simply the difference between the largest and the smallest values of a particular data set. And this is something that you should be familiar with based on some of your math classes. So if we take our two data sets here from our abalone rings and we compare the ranges, we can see that there's quite a bit of difference between these two, because the largest value for our first data set is quite a bit larger than the second one. And so we've got the same minimum value, but the maximum value is quite a bit different. Now, something to consider is that the range only incorporates two values in a data set, the minimum value and the maximum value. And so this limits us quite a bit in measuring dispersion. And this can also lead to misrepresentations of how variable our data set is. In the event that we happen to miss a particularly small or large individual, or if there's some type of migratory individual that happens to be included in our sample, this could drastically affect our measure of dispersion, potentially in our sample Y here, in which the range is 30 greater than Y star. And so similar to the mean, the range is highly influenced by outliers, by those extreme values that we observe in our data set. We're not going to spend too much time covering this in this particular lecture for the sake of time, but if you are looking for more information and practice, I'd check out section 4.3.1 and also bring it up in the lecture that you'd like to do some practice. Now, most of our measures of deviation occur in coordinates with the mean, in which we look at the difference between our representative data and the mean itself. So we can take our individual data points or observations and we can subtract the mean from them, and we can get an understanding of how variable our data set are. However, we run into a problem here. If this red line represents the mean of our data, we'll have an equal number of observations to the left and to the right of this. And so if we end up trying to summarize all these different deviations from the mean, our summation is going to be 0. So this is a bit of a problem because regardless of the data set, we're going to have this summation equal 0. So it's not going to be a good representation of how variable the data are because these negative and positive values counteract one another. But we can use this idea to get a better understanding of deviation if we add a couple wrinkles to the story. And so one of these wrinkles is going to be to divide our data not into halves but into quarters. And these are going to be called quartiles and provide us with a way that we can understand how much our data vary from central tendency. So for this particular measure of dispersion, we have 3 different quartiles: quartile 1, quartile 2, quartile 3. And these represent different percentiles in which there's 25% above and below these particular values. So we can think about these quartiles as percentiles, in which the first quartile, we've got 25% of our data that are less than this, and then the rest of our data are greater than that value. Our 50th percentile, or quartile 2, is the same as our median. This is our middle value for the data set, and 50% of our data are going to be less than this value, 50% are going to be more than this value. In our third quartile, the 75th percentile, is going to have 25% of our observations will have a greater value than this. The rest of the data will be less than this particular value. And we can use these quartiles to get an understanding of dispersion, particularly the range between quartile 1 and quartile 2, which is going to be the inner 50% of our data. And if we look at this particular histogram, what we notice is that the range of this particular group of data tends to be less than the outer 50% of the data. And we can use this inner 50% of the data to get an understanding of how much variability we have in our data, such that the greater this purple box would be, the more variability we would have in our respective data. So we can use this to quantify what we call the interquartile range. It's the distance between quartile 3 and quartile 1, so that any inner 50% of the data. And just for reference, again, the second quartile refers to the median. These are the same. So let's talk about how do we quantify these quartiles and use them. So the first step is going to be to rank order the data, same as the median, something that we're familiar with. The second is going to be to use this particular formula. It's quite similar to the formula for the median, except our denominator is 4 instead of 2 in this particular case. Now, similar to the median, if this value happens to be an integer, then our quartile 1 is going to equal the value for that particular integer. If it happens to not be an integer, if there's a decimal place, then we need to take into account the difference between the two values that this data point falls within, similar to the median. So how does this work? So we've got 16 different observations here from 2 to 20. And if we're interested in calculating the median, we use our formula of n plus 1 divided by 2, and we find that our median is our 8.5 observation. So between observation 8 and observation 9, we take the average of those observations and we get our median, 10.5. Now, this should be familiar to you. If not, go back to the measures of central tendency and watch that video again. Now, if we're interested in quantifying quartile 1, we make a slight adjustment to our formula, and our denominator is 4 rather than 2. So the observation 4.25 is our quartile 1. Now again, this isn't an integer, so we need to take into account the differences between our 4th observation and our 5th observation in this particular case. If we think about this on the number line, if we were thinking about the median, we would simply take the average of 6 and 8, but we're not interested in the median in this case. We're interested in quartile 1. Our decimal place is 0.25. So if we think about the distance between 6 and 8, we take 0.25 of that distance and we add that to 6. That will then become our quartile 1. So let's go through an example here and see how this works. Say that we're interested in measuring our oysters. We've got our frequency distribution table here, and we want to measure the quartiles and the interquartile range to get an understanding of dispersion in our data set. So we have our formula here after our data has been ranked ordered, and we enter in n of 24 to quantify quartile 1. So we get a value of 6.25 for this particular situation. So somewhere between observation 6 and observation 7. If we then go through and figure out which these two observations are, observation 6 and observation 7, they both happen to have the same value, 3.8 centimeters. So we don't need to do any math in this particular situation. Our quartile 1 is 3.8 centimeters. If we're interested in quartile 2, this is the same as the median. So we can use our formula for the median if we want, or we can simplify things if we've already calculated quartile 1 and multiply quartile 1 by 2. So let's do that and use that particular method since we're already familiar with measuring the median. So we can go through, we've got our quartile 1, which is the 6.25th observation, multiply that by 2, so our quartile 2 is the 12.5th observation in our particular data set. So it's halfway between observation 12, and observation 13. Now observation 12 and 13 both happen to be 4 in this particular situation, so our quartile 2, or our median, is 4 for this particular data set. For quartile 3, again, we have a variety of different ways to measure this, but the way I prefer to do so is to multiply quartile 1 by 3. So let's do that. So we can take our quartile 3, multiply that by 3, and quartile 3 is 18.75th observation. So quartile 3 is 3/4 of the way between observation 18 and 19. And this is important in this particular case because observation 18 and 19 are different. So first step here after we get our observation number 18.75 is we take the difference between the two observations that border this particular observation number, 18 and 19. If we take this, the difference is going to be 0.1 because our observation 19 is 4.2, observation 18 is 4.1, so the difference is 0.1 centimeters. We then take that and multiply it by the decimal or the fraction between which the quartile 3 lies between these observations. So in this particular case, 0.075. We'll take that value, 0.075, add it to the smallest value, 4.1, and we get our quartile 3 value. Now we move through this relatively quickly. We're going to go through another example in a minute, and we'll also be going through this in class, but I'd encourage you, if this was too quickly, to go back and to work through the video and also the PowerPoint lecture to make sure you understand how to calculate these values. Now, if we're interested in describing dispersion, we would then quantify the interquartile range, which would be the difference between quartile 3 and quartile 1. So in this particular case, our value for dispersion would be 0.375. If it were to be larger, it would indicate that we'd have more variability in the data, and if it was smaller, we'd have less variability in the data. Now, oftentimes we can graphically display this using a box and whisker plot. So we're going to talk about this in a little bit more detail because you'll want to be comfortable both drawing as well as interpreting these types of graphs, just like in the previous lectures for our data visualization. So when we look at a box and whisker plot here, this line in the middle of the box represents the median, or quartile 2. And then the outer portions of this box represent quartile 3 and quartile 1. So the larger the interquartile range, the larger this box is going to be, and the more variability that we have. So for comparing boxes to each other, we can tell which data set has more or less variability just by looking at the area of the box. Now, one other thing that we can look at that's often represented in our box and whisker plots is the mean. Now, rather than the line representing the mean, the line represents the median, there's usually an X in this box, and this is what represents the mean. And we can compare the mean to the median to get an understanding of the shape of our distribution, the shape of our data. Again, remembering that if our mean is greater than our median, well then our data is probably positively skewed or right skewed. Whereas if our mean is lower than our median, well then our data is going to be left skewed or negatively skewed. So in addition to the mean, quartiles, and the median, we can also get an understanding of the range of our data using these whiskers. Now we have formulas in which we can calculate these whiskers, but this is less important in this particular class. More importantly is that you understand that the end of these whiskers represent the minimum and maximum values unless there are outliers. In the event that there are outliers, you'll see these data points either above or below the box and its representative whiskers. Again, these outliers are extreme values compared to the rest of the data set. And something important is that we can compare different boxes. We can see which have more variability and which have less variability. We can get an understanding of differences in central tendency, and we can also notice that there are outliers that can be either above or below those whiskers, or maybe there are no outliers in the respective data set. So at this point, what I would like you to do is to take a moment and pause, recap what we've watched. Okay, so we're going to go through and do one more example here in order to make sure everyone is comfortable with this. If at any point in time during the video things are moving too fast, pause, go back 10 seconds and rewatch that portion of the video. So we have data on lengths of fishes that we're interested in, these sheepshead minnows, and we've got a frequency distribution plot here. And we're interested in quantifying dispersion using our interquartile range. So we need to calculate quartiles 1, 2, and 3 and the interquartile range. So our first step is going to be to rank order the data. This is already done for us. And then we're going to use our representative formulas to calculate our quartile numbers. So we take the summation of our frequencies, this is our total observations, and we're going to put that into our formula for quartile 1. So 48 goes in where n, small n is, and we find that quartile 1 is the 12.25th observation in our data set. We can go through and count until we reach observation 12 and observation 13, which border the 12.25th observation, and we notice they have the same value, so our quartile 1 is 34 millimeters length. We can go through, calculate quartile 2, so either the median or multiplying 2 times the observation number for quartile 1. Let's go with that second option here. So quartile 2 is the 24.5th observation. We can go through and count out 24 and 25 observations. We notice they have the same length, so our quartile 2, or our median, is 40 millimeters in length. Finally, we can use the same process that we did previously to quantify quartile 3, multiplying quartile 1 by 3. So this would then be the 36.75th observation. We can go through and we can count observation 36 and observation 37. They both have the same value again, so our quartile 3 is 46. For our interquartile range, we take the value of quartile 3, subtract quartile 1, and then we get our interquartile range of 12. Now we went through this relatively quickly. We'll be doing some practice in class, and I'd also encourage you to check out section 4.3.2 of your text for more detail. So this wraps up our description of how to measure range. The next video lecture rather, is going to cover variance and standard deviation.